Students, in previous lecture of this chapter sound, we have learned sound waves, that is longitudinal waves, and transverse wave. These are the types of the progressive wave. Even we studied the properties of the wave, that is amplitude, period, frequency, phase of the wave. And in today's lecture we are starting with the speed of the sound. Here, speed of the traveling wave is depend on the elastic property and density of the medium. Even we in previous lecture learned the properties of the medium. Three properties we studied. Now, for same medium, transverse and longitudinal waves which have different speeds. First, we'll try to learn how can we determine the speed of transverse wave. Now, the waves produced on the string are transverse waves. In this case, the restoring force is provided by the tension of the string. Transverse waves, the waves on the surface of the water, even the waves on the string, these are the transverse waves. And here, in case of the waves on a string, the restoring force is provided by the tension of the string. M be the mass per unit length of the string. Mass is capital M and length of the string is capital L. So small m is equal to M by L is the uh, mass per unit length of the string. By using these things, you can determine the speed of the sound of the transverse waves. Here V is equal to root T by small m. T is the tension of the string and m is the mass per unit length of the string. Now we'll try to determine the speed of the longitudinal wave. For longitudinal waves, we know that the sound is a longitudinal wave, travels through the medium in the form of compression and rarefaction. We already studied that when the longitudinal wave is passes through the medium is divided into compressions and rarefaction. The density of the medium is greater at the compression while smaller in the rarefaction. Hence, the velocity of the sound is depends on the elasticity and density of the medium. Here, the formula for speed of the longitudinal wave is V is equal to square root E by rho. E is the elasticity of the or proper modulus of elasticity of the medium, and rho is here, rho has to be considered instead of P. Rho is the density of the medium. Now, Newton's formula for velocity of sound. Sound waves travel through a medium in the form of compressions and rarefaction. We already discussed it. Then density of the medium is greater at the compression and being smaller in the rarefaction. It is possible only an elastic medium should be elastic. This is the property of the medium. And when longitudinal wave is passes through the elastic medium, the compressions and rarefactions is produces successively. Here the velocity of sound depends on the density and the elasticity of the medium, and it is given by V is equal to square root E by rho. E is the modulus of elasticity of the medium, and rho is the density of the medium. Now this is equation 1. Newton assumed that during a propagation of the sound wave in the air, average temperature of the medium remains constant. Means the this process, when the sound wave is passes through the medium, compressions and rarefactions is produces, and during the compressions and rarefactions, particularly in compressions, the heat is increases, but it is neutralized in the rarefaction. This is according to the Newton's formula for the velocity of sound. Newton considered this. Hence, propagation of the sound wave in air is an isothermal process. Isothermal elasticity should be considered over here. Therefore, uh, for a gas or air, isothermal elasticity E is equal to the atmospheric pressure P. This is the isothermal process according to the consideration of Newton. So isothermal elasticity E is considered as atmospheric pressure P. Therefore our equation becomes, that is equation 1 for the velocity of sound in air or the gas is considered as what? V is equal to root P by rho. Now E is replaced by P, that is pressure, atmospheric pressure of the air or gas. So we know that pressure P is equal to H d Z. H is the barometric height, and P is the D is the density of the air, and G is the acceleration due to gravity. So formula for the velocity is becomes root H d Z by rho. Now we know that the values of H, D and Z. For H it is 0.76 meter. This is the barometric height, and density of air, it is 13600 kilograms per meter cube. Density of the mercury, density of the air is 1.293 kilograms per meter cube, and G is 9.8 meter per second square. Now if we use these values in the above formula, that is V is equal to square root H dz by rho, the value of velocity of sound in air is 279.9 meter per second at atmospheric uh, temperature pressure, sorry, neutral temperature, sorry, natural temperature pressure, sorry. This is the uh, velocity of sound in air by Newton's formula. But experimentally it is found that at a natural temperature pressure, the velocity of sound in air is 332, that is 332 meter per second, and by Newton's formula the velocity is 279.9 meter per second. So there is the considerable difference between the value predicted by the Newton's formula and the experimental value of the velocity of sound in air. Laplace is the scientist. He corrected the Newton's formula. So we'll try to learn the Laplace formula for velocity of sound in air. Laplace correction. Laplace suggested that the compression or rarefaction takes place too rapidly. So heat produced during compression and loss during rarefaction does not get sufficient time for dissipation. Here Newton assumed that the heat is dissipated, and Laplace correction is what this compressions and rarefactions which is produces in the medium, it is very fast, so no dissipation of the heat is there between compressions and the rarefactions. So this process is the adiabatic process. Due to this, whole heat is constant and remains same. So it is adiabatic process according to the Laplace. So E is adiabatic modulus of elasticity of air medium, which is given by, now there is the correction. E is replaced here, E is replaced by P, atmospheric pressure, that is H dz. Laplace suggested that this gamma should be there with P. What is gamma? Gamma is the ratio of the specific heat capacity at constant pressure to the specific heat capacity at constant volume. Uh, so here this is equation 1, and uh, P is the pressure of the air medium, gamma is the ratio of the specific heat of air at constant pressure, and specific heat of air at constant volume. The ratio of these two, that is specific heat at constant pressure to the specific heat at constant volume, is a constant, and it is gamma. So for adiabatic process, this gamma is 1.4. Okay, so our equation is V is equal to root E by P. E is replaced by gamma P according to the Laplace correction. Now here E is replaced by gamma P. Equation becomes V is equal to root gamma P by rho. Again here P is H dz, but value of gamma, that is a ratio of the specific heat at constant pressure to the specific heat at constant volume, is 1.4. So next, by using values, gamma is 1.41. For natural temperature pressure, it is P is equal to 0.76 into 13600. This is the uh, density of mercury. Density of air is this, that is 1.293 and G is 9.8. Using this data in the above equation, we'll get V is equal to 332.35 meter per second, and this is the value which is close to the experimental value. So this is the Laplace correction. Even we study the Newton's law for velocity of sound in air, or Newton's formula for velocity of sound in air. There is the correction in Newton's formula, and this correction is done by Laplace. Therefore Laplace correction, this special article has to be considered here. Now next is effect of the pressure on the velocity of sound. Let V be the velocity of sound in air when pressure is P and density is rho. Using Laplace formula, we can write, using Laplace formula, we can write V is equal to root gamma P by rho. Gamma P by rho. Now here V is the velocity of sound in air, P is the pressure, rho is the density, and according to the Laplace correction, gamma has to be consider because it is a adiabatic process. Now uh, rho is the density of the air, and it is m by v. M is the mass and v is the volume. So this rho is replaced. Our formula becomes v is equal to root gamma pv. V is to the denominator, so it becomes pv by m. Now according to the Boyle's law, we know that this pv is constant at constant temperature. Also mass of the air or mass of the gas is constant, gamma is constant, so velocity of sound in air will be remains constant, means there is no change in velocity of sound in air when pressure is changes. Okay, it not depends on the pressure as long as the temperature remains constant. There is no change in the velocity of sound uh, if the pressure in the air is changes. Then if we consider the ideal gas equation, PV is equal to nRT, then our formula is becomes V is equal to root gamma nRT. Instead of PV we'll write nRT by m. For this also, for gaseous medium, uh, for the ideal gas equation, if we consider the ideal gas equation, the velocity of sound does not depends on the change in pressure as long as the temperature remains constant. If the temperature of the atmosphere is the constant, there is no change, then the if the velocity of sound in air remains constant, there is no change in the velocity. The next is effect of the temperature on the velocity of sound. Effect of the temperature on the velocity of the sound. Suppose V naught is the speed of the sound at temperature T naught, initial temperature and uh, initial speed of the velocity of the sound. Then V is the speed of the sound at uh, T in kelvins respectively. That time rho naught is the density. When temperature, initial temperature T naught, uh, speed is V naught, and density of the air or density of the gas is rho naught. Temperature changes, there is the increase in temperature. That time the speed is V and density is rho. Definitely in previous article we learned that when temperature is constant, there is no effect of the pressure on the velocity of the sound. If the temperature is changes, then the velocity and the density of the air is changes. So here we have to consider this at initial temperature, the velocity of or the speed of the sound is v naught, and it is equal to uh, root gamma r t naught by m by using Laplace correction. And here every time we have to consider the equation for velocity of sound, that is v is equal to root gamma p by rho. Then rho is replaced by m by v, that is density is mass per unit volume. V is in numerator, it becomes gamma pv, and again using ideal gas equation, this PV is replaced by RT for n is equal to 1. So our equation becomes root gamma RT naught. Now initial temperature has to be considered, divided by m. This is the equation. Now when temperature is changes, the speed of sound is v, and it is equal to root gamma rt by m. Then ratio of these two equations, v by v naught, v by v naught, m cancels, rt by even gamma cancels. Okay, uh, gamma and the m cancels, even r cancels, and we'll get the formula, that is the ratio of the velocity of sound at different temperature. V by V naught is equal to root T by T naught. Now change in the speed of the sound you can determine by rearranging this equation. That is V is equal to root T by T naught into V naught. That is initial velocity when temperature is T naught, initial temperature. So here from the equation it is clear that the velocity of the sound or speed of the sound is directly proportional to square root of the temperature, atmospheric temperature. Okay, so this is the conclusion by effect of the temperature on velocity of sound. The next one is the effect of humidity on the velocity of sound. What is humidity? Moisture in air, and it depends on the presence of the water vapors in air. Humidity is the moisture, and it depends on the presence of water vapors. Here rho m is the density of moist air, and PD is, sorry, rho d is the density of dry air. Similarly, we have to consider what Vm is the speed of the sound in moist air, and Vd is the speed of sound in dry air. This has to be considered. Now again the formula has to be considered, that is speed of the sound in moist air is root gamma p by rho m. Rho m is the density of the moist air. Similarly, we'll write for uh, the speed of the sound in dry air. So the formula is Vd is equal to root gamma p by rho d. Rho d is the density of dry air. Again, we have to take the ratio, that is speed of moist air to the speed in dry air. So it is equal to uh, root rho d, that is density of dry air to the density of moist air. So this way we will find the uh, speed of the sound air in moist air and the dry air by rearranging the above formula. So moist air is always less dense than the dry air. This is about what by using the humidity you can determine the velocity of sound in air. Now the next important article from the chapter is Doppler's effect, but here we are considering this Doppler's effect by using the formula. Other derivations I am skipping over here. So we'll try to learn the Doppler's effect with formula. Doppler's effect we'll learn in two parts. One is the Doppler's effect in sound and Doppler's effect in light. So in Doppler's effect in light wave, with light waves, we'll learn in 12th standard. Here Doppler's effect uh, in sound waves. The statement is the apparent change in the frequency of sound heard by a listener due to relative motion between the source of sound and the listener is called Doppler's effect in sound. Apparent change in frequency is occur when there is the relative motion between the source of the sound and the listener is the Doppler's effect in sound. The statement is very simple, and here we have to consider some um, constants. Uh, N naught is the actual frequency of the source. Natural frequency of the source is N naught, and N is the apparent frequency of the source. When there is the relative motion between the source and the observer, there is the decrease or increase in the frequency of the source is there, and this frequency is small n. V is the velocity of sound in air, Vs velocity of the source, and Vl is velocity of listener. This is the simple constant. Then general equation for the apparent change in frequency is occur will be determined with this, that is n is equal to n naught. Now n is the apparent frequency, n naught is the natural frequency of the source, v is the velocity of sound in air, vl is the velocity of listener, and vs is velocity of the source. When uh, the positive sign in numerator and negative sign in denominator is considered, then the apparent frequency is increases. Definitely denominator is less than the numerator, the apparent frequency will be increases. That time the source and listener is moving towards each other. And if we consider the negative sign in numerator and positive sign in denominator, definitely this ratio will be less and apparent frequency is decreases. The observer, that is listener, and source of the sound will move away from each other. So equations by using Doppler's general equation, n is equal to n naught into bracket v plus minus vl divided by v minus plus by vs. This is the general equation, and here clearly mention what the positive sign in numerator and negative sign in denominator is considered, then the listener and the source of sound will move towards each other and apparent frequency is increases. Definitely if we consider the negative sign in numerator and positive sign in denominator, this ratio is decreases as I said, so apparent frequency will be decreases. Source and the observer, that is listener, will move away from each other. So equation is this. Now more cases are there. If the source is moving and listener is stationary, so VL, that is velocity of the listener, is becomes 0, and the equation is n is equal to n naught v by v minus vs. Now source of the sound is in motion and listener is constant, that is vl is equal to 0. Apparent change in frequency is increases because denominator is less and numerator is more, so this ratio is uh, definitely uh, greater than 1. So apparent change in frequency is increases, the source is moving towards listener. Okay, next case is what? Now listener is stationary, but source is moving away from the listener. Then apparent change in frequency is decreases. Definitely that time numerator is greater than, sorry, denominator is greater than numerator, and this ratio is less than 1. This will be plus V plus Vs. Then the apparent change in frequency is decreases. Definitely source will be moved away from the listener, and the equation is n is equal to n naught V by V plus Vs. Two more cases will be considered. Here listener is stationary and source of the sound is moving towards the listener. Apparent frequency is increases, and source move away from the listener, the apparent frequency will be decreases. Similarly, we consider one more case. If the source of the sound is stationary and listener is towards the source of the sound, okay, so the case is what, listener is moving towards the source, then apparent change in frequency definitely increases. Now here plus V plus VL means numerator is greater than the denominator. This ratio is greater than 1. Therefore, apparent change in frequency is increases, and the listener is towards the source of the sound. Patch of the frequency of the sound is increases. Now, if the listener is away from the source of the sound, definitely the frequency, apparent frequency will be decreases. This numerator will be with minus sign. So our equation is n is equal to n naught V minus VL by L. This ratio will be less than 1, and apparent change in frequency is decreases. Listener is away from the source of the sound. So these are the cases, and from these different cases you can learn Doppler's effect in sound. So this is the different topics which is included in our uh, chapter sound, and we are closing here the theoretical part of the chapter. We'll try to learn the simple topics in better way in the chapter. So we'll stop here, and in next lecture we'll try to learn examples on this chapter. Thank you.